we need to talk about why. Why does the TLC plate do what it does in a laboratory? Why does the TLC plate separate components the way that it does? And when I inject a sample, can I maybe predict which compounds will go up further and which would stay down below? Those are the questions that we're going to have to start answering. And this video is going to be kind of the first time with me explaining how this separation process begins to take place in a TLC plate. So we've talked about the stationary phase in a TLC plate. And we said that this is either going to be silica, SiO2, or alumina, Al2O3, also called aluminum oxide. All right, so whichever one of these two are chosen, silica is going to be the majority of the time. 70 to 80% of the TLC plates are typically silica-based. If it's silica or if it's alumina, and these two are the ones that make up the majority of the TLC world, both of these stationary phases are polar. Okay, so if you need review of polarity again, that basically means that this silica, the way that it's structured, has all of these electrons around our oxygens, right? That's the deal here. And there's even silica electrons around the center of the molecule as well. So there's negative areas all over the place. And we took a look at the silica stationary phase as far as the surface of the stationary phase goes. And we see this oxygen and silica and oxygen and silica and oxygen and silica repeat over and over and over. And then off of each one of these silicas, we said that these stationary phases will typically be loaded with a hydrogen at least, just to cap off that outside layer of the oxygen with an OH, something simple. All right, well, polarity is everywhere. So therefore, when we inject samples on a TLC plate, the more polar the samples are, the more they're going to hang out with the stationary phase. So they're going to love the stationary phase if they are polar compounds. If they love the stationary phase, that means that these things will be held back. And that's the whole issue with chromatography anyway, right? We're talking about holding things back. So if we have an assortment of samples that we have injected or we have loaded on a TLC plate, then I need to look at the polarity of these compounds. I need to figure out which one is more polar than the other. Is there a way that I can determine that? And whichever one is the most polar, that's the one that's going to be stuck to the stationary phase a little bit longer. And that's the one that's going to be held back on the TLC plate a little bit more. Well, in the TLC world, what that's referring to is how far the spot travels up the plate. So let's see that this is my starting line. And I've spotted a sample A and sample B. And then migration has happened. I've developed my TLC plate. And this piece maybe comes here, and this piece comes here. All right, well, those are my samples, and I can do all kinds of calculations with them if I want to, and we'll eventually get to those calculations. But right now, we need to talk about why things move the way that they did. So if I look at sample B, this has not moved as far as the sample A has. So this is lower. And lower means that it really liked the stationary phase. It wanted to hang out with the stationary phase a little bit more. It was harder to get that compound to dislodge and move up the plate. So it prefers to be on the stationary phase. If it prefers to be on the stationary phase, then that means in this case, B is more polar than my A compound. So if I have a group of compounds in the very beginning and I know what their structures are, and you'll know that in your first TLC lab that you do, but if you know the structures of them, then you can actually look at these structures and determine which one is the most polar. Whichever one's the most polar, that's going to be the lowest traveling one on the TLC plate. Whichever one has moved the furthest, that's going to be your most non-polar molecule because it doesn't like the stationary phase. It doesn't hang out with it as much. So it prefers to be on the move with the mobile phase. So this is kind of an introduction of how things begin to separate and move in a TLC plate. Now, this is not the only thing that we talk about. Right? Just like in the previous video, we said that polarity was the number one player here. But you know, there's other players at stake too, and this is basically our solvent system. What kind of solvent are we using? Because that's going to be important. And then we can talk about electronegativity. That's important as well. It's related to polarity, but we can also talk about electronegativity in a different way, in a different fashion. And then we can talk about these intermolecular forces like we mentioned in the last video. All right, all of these are very important. They all play a role in the separation. But if you wanted to start somewhere, if you needed a launching point, and if you needed a way to describe why things are separating the way that they are, and why things are moving in a TLC plate the way that they are, it's all due to polarity. That's kind of the number one rule that we go by every single time when we talk about separation in a TLC plate. So please keep that in mind because you're probably going to get some test questions. And those test questions are basically going to talk about which of these molecules would move the furthest. And I'll give you some structures and maybe some compounds to choose from. And then the next part of that question is going to be why. Why did you choose that one? And you need to make the argument for polarity. That's why this thing works the way that it does. So it is safe to say that the most polar compounds will be the lowest on the TLC plate, and the most non-polar compounds will be the highest on the TLC plate. Now, you might not get that correct every single time, but for my test, for my quizzes, for our labs, what we do is very simplistic in nature. There's no kind of funny research stuff going on, and we can make this general argument every single time. Even though it's only one part of the argument, we can make that argument every time. Okay, another thing that will play a factor here, you've got to be really careful. Yeah, we can summarize this and we can say polarity has everything to do in the world with it, but one of the things that people forget is pH, right? pH is very important in the TLC world. pH can really change whether a molecule is polar or not polar. So, for instance, if I've got a functional group on a molecule, and let's say that I've got an OH group, that OH group is polar, right? But after a certain pH level, this hydrogen can actually kick the curb. And what we'll end up with is maybe a complete negative now on the oxygen. All right, well, that's an issue that we have to deal with because now I have a larger charge on the molecule, and that larger charge means that that molecule is now even more polar than what it was before. So pH plays a role in polarity, especially in the world of TLC. The same thing can happen in another way. Let's say that I have an NH2 group on a molecule. That NH2 group, the amine functional group, can actually accept protons. And it can accept protons all the way up to a certain point. So depending on my pH, this thing could be an NH3+, or it could be just an NH2. Well, both of these are basically polar, but the NH3+ is even more polar than what it was before. So again, pH has played a role in the polarity of a molecule. So don't be surprised if the instructions on a TLC lab will talk to you about adjusting the pH. It will say, take your mobile phase and make sure that your pH is between this value and this value. And as long as it is, you're good enough to run. That is the reason that they're telling you to do that in a laboratory. The pH dependency is very important when it concerns polarity, because it can make these molecules do funny things that they couldn't do before, and these are to carry full-blown charges on the molecule. And that could really switch up the order of what you would expect when you develop these samples on a TLC plate. So, keep pH in mind. It does change molecules. It can affect the order of which things run. And you might be forced to adjust some pH in a laboratory at a certain point in time.